Welcome students. Today in this session we shall familiarize on the topic gaseous state. Gas, as you all know, it is everywhere around us, right? From circling our huge planet to creating various layers in our atmosphere and covering the Earth's surface in vast square kilometers beneath the foundations of the land that we live in, and finally running through the very air that we breathe in, isn't it? So relating with the gas and its properties, have you ever had an idea why a balloon inflates as we feel air within it, or why a fragrance of a flower spreads out in the air slowly? Okay, so in this session what I aim is to impart you a basic and concise insight on the gaseous state. You might have already studied in your lower classes about different laws of the gases like Boyle's law, Charles' law and Avogadro's law. These laws hold good for all gases irrespective of the nature and are based on experimental observation. In order to understand as well as explain the nature and behavior of gases at the molecular level, it is James Maxwell who proposed kinetic molecular theory of gases. The theory also takes into account the molecular concept of matter as well as the motion of particles. The kinetic molecular theory basically states that all matter consists of atoms and molecules which are always in motion. That means these particles have some amount of kinetic energy. In higher temperatures, the particles have high energy, and in lower temperature, the particles have less kinetic energy. The more energy the particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are contained within. But for the case of gases, the steam itself for an example, the particles have most energy. These particles move around freely in random motions. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. Thus, unlike solids and liquids, gases are random groups of atoms that are spread out, and these atoms and molecules are full of energy bouncing around constantly. The kinetic molecular theory of gases can explain the macroscopic properties of gases such as volume, pressure and temperature, as well as transport properties such as viscosity, thermal conductivity, mass diffusivity, etc. This model also accounts for related phenomena such as Brownian motion. We will come detail into this. Before that, we shall have a look on the various postulates that explains the kinetic molecular model of gas as explained by Maxwell. First and the foremost postulate is that all gases consist of a very large number of minute particles called molecules. These molecules are extremely small in size and are separated by large distances, due to which most of the volume of the gas occupied consists of empty space. Thus, the actual volume of the gas molecule is negligible as compared to the total volume occupied by the gas. And this observation also means that the volume occupied by the individual gas molecule may be ignored. And this postulate explains the compressibility of the gas, that is the ability of a gas to reduce its volume on application of pressure. For instance, we can easily squeeze an empty closed bottle as the air inside it gets compressed and as we apply pressure externally, isn't it? Similarly, we can also squeeze a balloon to a smaller size when pressure is applied, right? The reason is that the empty space between the molecule decreases, so we can say the compressibility of gases abide with the first postulate of kinetic gas theory. The next postulate of kinetic theory is that the pressure exerted by the gases due to the bombardment of the molecules on the walls of the container. That is, when a molecule strikes the walls of the container, it exerts a little force per unit area. That is what you mean by pressure on it. The total pressure, what is the result of the hits due to all the molecules per unit area, gives the pressure of the gas. Next postulate of kinetic gas theory says that the gas molecule collide with one another and also with the walls of the container. These collisions are perfectly elastic and there is no loss of energy during these collisions. Suppose if we think that the molecular collisions are not perfectly elastic and as a result the molecules will lose energy at each collisions, therefore the kinetic energy will go on decrease and ultimately becomes 0. That means that molecule will come to rest and should settle down at the bottom of the vessel. And since the molecule come to rest, they will not collide on the walls of the container and the gas should show no pressure. But this never happens, right? Hence, we say that the molecular collisions are perfectly elastic in nature. The next postulate says that the particles of gases, whether atoms or molecules, are not static and move randomly taking straight line paths. This movement of gas molecule in different direction is called Brownian motion. Their speed and direction change when these collide with one another or with the walls of the container. Explaining more clearly, suppose we are in a cinema theatre, the haphazard motion of the gas molecules can be observed in a beam of light falling on the cinema screen. The solid dust particles are hit by gas molecule present in the air and these dust particles come in haphazard motion known as Brownian motion. The next postulate of kinetic theory of gases states that the distance between the gas molecule is very large. There is no effective force of attraction or repulsion between them. Gases can be compressed on the application of high pressure, which can be considered as due to the force of attraction between the gas molecules. When the pressure is released, then gas fill with the wall space available to them. Hence, there is no effective force of attraction or repulsion between molecules. The other property of gas molecule is that the average kinetic energy of the gas molecule is directly proportional to the absolute temperature of the gas. For instance, when a gas is heated, the temperature of the gas increases. The speed and the average kinetic energy of the molecule increases. Thus, the average kinetic energy is directly proportional to absolute temperature. And the final postulate of kinetic theory gases is that there is no effect of gravity on gas molecules. Heavier gases do not form the lower layer in a mixture of gases. They form a homogeneous mixture due to the process called diffusion. This means that gravity has no effect on the gas molecules. Thus, these postulates explain the properties of gases at the molecular level. Okay. Now, let us see how these postulates lead to the derivation of kinetic gas equation or say simply the pressure of an ideal gas. Suppose in a cube contains n mole of a gas, the side of the container is L and hence the volume of the container is L cube. And students, so the volume of the gas is also L cube because the gas occupies complete space within the cube, isn't it? Also, the temperature of the walls are kept constant. Gas molecules are always in a state of constant motion and they collide with each other and with the walls of the container. Here, intermolecular force is supposed to be 0 because we are considering the case of an ideal gas. Now, consider a gas molecule moving with a velocity v about to collide on the opposite wall. We know that according to the kinetic theory of gases, these collisions are perfectly elastic. So, considering the wall A of the cube which is parallel to the YZ plane and the molecule's velocity component vectors are Cx, Cy and Cz. Velocity of a molecule can be resolved into its components such as C square is equal to Cx square plus Cy square plus Cz square. As the molecule hits the wall A, it rebounds and you can observe that only x component of the velocity vector is reversed, whereas the y and the z components remains unchanged. Thus, the y and z components remains always unchanged for all collisions parallel to YZ plane. So, change in momentum of the particle is due to x component only. Momentum of the particle before striking the wall A, if it is mcx, then after colliding the wall A, it will be minus mcx. So, change in momentum as you know is, it is final momentum minus initial momentum. Here final momentum is negative and hence momentum is negative and the initial velocity is positive and hence the momentum is positive. Thus, what we get is change in momentum per collisions per molecule of wall A is equal to minus mcx minus mcx, which is equal to minus 2 mcx, and the momentum transferred to the wall will be positive 2 mcx. Okay. Now, the molecule is reversed to hit the next opposite wall B and again rebounds to wall A to collide once again. In this way, that the molecule hitting the wall A and its momentum is changing, one can say that the molecule has to travel 2 into L distance to hit the wall once again. Hence, the Cx speed, the time interval between two successive collisions will be, that is, number of collisions in 1 second on wall A is equal to distance travel per second divided by distance between two collisions, which is equal to Cx by 2 into L. Momentum transferred on wall A per second per molecule is equal to, that becomes 2 mcx into Cx divided by 2 into L, which is equal to mcx square divided by L. The total momentum thus transferred to two opposite walls A and B along x axis will be 2 mcx square divided by L. Similarly, along y axis it will be 2 mcy square divided by L, and along z axis it will be 2 mcz square divided by L. So, the total momentum per second per molecule to all the walls of the cube will be equal to 2 mcx square divided by L plus 2 mcy square divided by L plus 2 mcz square divided by L, which is equal to 2 m divided by L into Cx square plus Cy square plus Cz square, which can be written as 2 mc square divided by L. But there are n number of molecules moving with different velocities c1, c2, c3, etc. So, the total momentum per second transferred to all 6 faces of cube by n molecules will be 2m divided by L into c1 square plus c2 square plus c3 square, etc., which is equal to 2mn divided by L. That is, we can rearrange the equation to c1 square plus c2 square plus c3 square, etc., the whole divided by n, which is equal to 2mnc square divided by L, where c is the root mean square velocity of the gas. Now, 2mnc square divided by L is the total momentum transferred per second, that is, it is the force itself. That is, we can write the equation as 2mn c square divided by L, which is equal to P into A, that is pressure into area. That is 2mn c square divided by L is equal to P into 6L square, because the area of the cube is 6L square. Now, rearranging the equation, we can write it as 2mn c square divided by 6L cube, which is equal to pressure. That is 2mn c square divided by 6V, which is equal to pressure. So, finally, we can write this equation as PV is equal to 1 by 3 mn c square. That is, PV is equal to 1 by 3 mc square also, because m here is the molecular mass. So, that is equal to mass of one gas molecule into the Avogadro number n. So, it can be written in the form as PV is equal to 1 by 3 mc square also. Also, we know that density of the gas is equal to mass by volume. That is, we can write this equation in the form P is equal to 1 by 3 dc square. Okay, these three equations, all we can say it is some form of the kinetic gas equation. Now, let me ask you one question. How do you understand the relationship between kinetic energy and temperature from this kinetic gas equation? We know the kinetic gas equation is PV is equal to 1 by 3 mn c square. Okay. So, now we are including, or we are multiplying the equation with 2 and dividing with also 2. So, we can write the equation as PV is equal to 2 by 3 into 1 by 2 mn c square, and this 1 by 2 mn c square term itself is kinetic energy. So, the equation becomes PV is equal to 2 by 3 kinetic energy, and PV is equal to RT for 1 mole of a gas, as we know, isn't it? So, RT is equal to 2 by 3 kinetic energy. That means kinetic energy is directly proportional to temperature. The kinetic energy of the gas is directly proportional to its absolute temperature and is independent of the nature or pressure of the gas. Now, we shall look into how the gas laws are easily derived from kinetic gas equation. Considering first Boyle's law. We know that the molecular velocities increase with rise in temperature. Since kinetic energy varies as square of velocity, it is possible to define temperature in terms of kinetic energy. Thus, according to kinetic theory, the absolute temperature T of a gas is proportional to the mean kinetic energy, that is half mc square per molecule. It is thus evident that at a constant temperature, the mean kinetic energy per molecule of any gas remains constant. The kinetic gas equation may be written as PV is equal to 2 by 3 into 1 by 2 mnc square. It is a definite mass of a gas is under consideration, then the number of molecules n of the gas must also be constant. It follows therefore that for a given mass of a gas at a constant temperature, the quantity on the right hand side of this equation must remain constant. Hence, PV is equal to constant. Thus, PV is constant at constant temperature, and this is actually what Boyle's law states. Now, coming to Charles' law, for a definite quantity of a gas, that is n equal to pressure may be written as a constant, the equation becomes PV is equal to 2 by 3 into half mnc square, and this can be written as V is directly proportional to half mc square. The quantity half mc square being the mean kinetic energy per molecule varies as the temperature T as discussed previously. Hence, V is proportional to T at constant pressure. Thus, at constant pressure, the volume of a given mass of a gas varies directly as the absolute temperature, and this is what Charles' law states. Similarly, we could derive other gas laws from kinetic gas equation such as Avogadro's law, Graham's law of diffusion, and also Dalton's law of partial pressures. Okay, now let me ask you one thing. Can we apply this kinetic gas theory to all gases at all conditions of temperature and pressure? Okay, we shall now discuss on how this ideal behavior is deviated for real gases. As already discussed earlier, the equation PV is equal to nRT derived from kinetic gas theory is valid for ideal gases only. Real gases actually obey this equation only approximately, and that too under conditions of low pressure and high temperature. The deviation from ideal behavior will become more and more greater at high pressures and lower temperatures. It is generally seen that the most easily liquefiable and highly soluble gases show much greater deviations from being an ideal gas. Thus, we could say that, for example, carbon dioxide, sulfur dioxide and ammonia are some examples that show greater deviation than when compared to gases like hydrogen, oxygen and nitrogen. So, how do we represent this deviation of real gases from behaving ideally? Usually, the deviation of real gases from ideal behavior is best represented in terms of compressibility factor or so-called compression factor Z, which is defined as Z is equal to PV divided by PV ideal, which is equal to PV divided by nRT, which is equal to PVM divided by RT, where Vm is equal to V by N is the molar volume, that is the volume occupied by 1 mole of a gas. So far, for the case of ideal gases, the value of Z is equal to 1 under all conditions of temperature and pressure. The deviation in value of Z from unity can be thus considered as the extent of deviation of real gases from ideal behavior. Here we can see the graph plotted for compressibility factors determined for a number of gases over a range of pressure at a constant temperature. At extremely low pressure, all gases have values for Z close to the unity and behave almost as an ideal gas. As the pressure is increased, the deviation is also increased at very high pressure, and all gases have Z more than unity, indicating that the gases are less compressible than an ideal gas. And this is because at high pressure, the molecular repulsive forces are dominant. From the figure, we can also see that at moderate low pressures, Carbon dioxide, methane and ammonia are more compressible than an ideal gas. That is, Z is less than 1 as PV is less than PV ideal. This is due to the fact that at low pressures, the long range attractive forces are dominant and favor compression. The compressibility factor Z goes on decreasing with increase in pressure, passes through a minima at a certain stage and then begin to increase with increase in pressure. The gases now become less compressible than an ideal gas, that is PV is more than PV ideal. So, that Z is greater than 1. It is evident from the figure that while carbon monoxide and methane exhibit marked deviation from ideal behavior only at high pressures, ammonia shows larger deviation even at low pressures. Now, if we consider the effect of temperature on deviation from ideal behavior as from the figure, showing that the plot of compressibility factor against pressure for hydrogen gas at different temperatures varying between 60 Kelvin to 333 Kelvin, and it is seen that as the temperature is rise, the dip in the curve becomes smaller and smaller. At 333 Kelvin, the curve seems to remain almost horizontal for an appreciable range of pressure, showing thereby that the compressibility factor is that become almost equal to unity under these conditions. In other words, the product PV remains constant and thus Boyle's law is obeyed within this range of pressure at 333 Kelvin. This temperature is called boil point or boil temperature. Below this temperature, the value of Z at first decreases, approaches a minimum and then increases as the pressure is increased continuously. Above 333 Kelvin, the value of Z shows a continuous rise with increasing pressure. So, now why real gases show such deviation from ideal behavior? The explanation for the deviation from ideal behavior by real gases is that the two postulates of kinetic theory do not hold good under all conditions. We have already discussed that the first postulate stating that the volume occupied by the molecules themselves is negligibly small as compared to the total volume occupied by the gas. This postulate can be justified only under ordinary conditions of temperature and pressure. It can be shown by calculations that in some of the common gases, the volume occupied by the molecule themselves is under ordinary condition, that is only 0.14% of the total volume of the gas. This is a negligible fraction indeed, but if the pressure becomes too high, say like 10 atmosphere or more, the total volume of the gas will decrease appreciably, whereas the volume of the molecule will remain almost the same because the molecules are incompressible. Hence, under conditions of high pressure, the volume occupied by the gas molecules will no longer be negligible in comparison with the total volume of the gas. The same thing happens when the temperature is lowered to a larger extent. The total volume of the gas decreases considerably, no doubt, but the volume occupied by the molecules themselves remain practically the same. In this case too, the volume occupied by the molecule will no longer be negligible. The first postulate of kinetic gas theory is therefore not valid at high pressures and low temperatures. The second postulate of kinetic gas theory is that the forces of attraction between gas molecules are negligible. This assumption is valid at low pressures and high temperatures because under these conditions the molecules lie far apart from one another. But at high pressures or at low temperatures the volume is small and the molecule lie close to one another. The second postulate of kinetic gas theory is that the forces of attraction between gas molecules are negligible. This assumption is valid at low pressures or at high temperatures because under these conditions the molecules lie far apart from one another. But at high pressures or at low temperatures the volume is small and the molecule lie close to one another. The intermolecular forces of attraction therefore are appreciable and cannot be ignored. Hence, the second postulate also does not hold good under conditions for high pressure and low temperature. From this, we understand that it is necessary to apply suitable corrections to the ideal gas equation so as to make it applicable to real gases also. This will be our topic of discussion in the next section. So, with this I am concluding this session. Thus, today we have discussed different postulates of kinetic theory of gases, derivation of kinetic gas equation, followed by the deviation of real gases from ideal behavior and the causes of deviation. In the next session, I will be talking on van der Waals equation of state for real gases, derivation of ball temperature, critical constants of gas and law of corresponding states. Hope the concept on gaseous state I have taken so far is clear to you. Thank you.